Luc Hillairet from Université d'Orléans, and he will tell us about heat asymptotics of Sub-Riemannian structures. Thank you.
Okay, so thanks, Stefan. So first, I would like to thank the organizers for inviting me to give a talk in this terrific conference. So the first word is not okay. It's what it is. I will try to explain it, what it means, and I will begin by introducing the setting. So everything I say will be on a smooth, compact, connected manifold. And of dimension d. And mu is a smooth measure on it. So for reasons that will be clear maybe right now, I need to fix a smooth measure, which is the first difference between sub-Riemannian geometry and Riemannian geometry. So what is a sub-Riemannian structure? So there are different definitions. I will use the following definition. I will denote by xi, I between I and 1 and k, to be smooth vector fields that are globally defined on M. And my aim is to study the following self-adjoint operator, which is delta, which is the sum from I equals 1 to k of xi star xi, and where the adjoint is taken with respect to u. So there is no a priori relation between the number of vector fields that you take and the dimension of the manifold. So, but what you do is I should perhaps motivate a little bit what Sub-Riemannian geometry is. So Sub-Riemannian geometry is a geometry in which you're not allowed to go into any direction. And so despite the fact that there may be more vectors than at a given point, there may be more vectors than the dimension of the manifold, the span of these vectors will be strictly, or not strictly, will be less than d. And in order to get the missing direction, what you need to do is to make bracket, so like when you park your car, and so you define d1, which is the span of the xi at each point q, and now you iterate the construction by constructing a flag of vector space in the tangent space by adding to each di the commutators with d1. So probably this is what Clotilde called a filtered thing. And the standing assumption in this business is what is called Hermander's bracket generating condition. So I will ask it to be uniform with respect to the point. So there exists some R such that for all q in M, d R at q is a full tangent space. So let me give you right away two examples that I will use later. So the first one is what's called a Heisenberg structure. So my compact manifold is R3. So meaning that I have taken some, so actually a ball in R3 if you really want it to be compact. And I take coordinates u, v, w, and my first bracket is du, and my second bracket is something like x2, which is dv plus u times a of u, a of vw, why not, dw, and I assume that this function a is positive everywhere. And so, of course, you cannot generate the tangent space because you only have two vectors. But if you do the commutator of x1 and x2, then you will have a of vw dw that will give you the missing direction. So that's my first example. And then I have a second example. So these are the first two basic examples in any Sub-Riemannian geometry course. These are the first two things that you will encounter, or maybe depending on. Okay. So the second one is what I call a Bowen-Digrushin plane. Structure. So this times I'm in R2. X1 is also du, and now X2 is u times a of v, a of uv dv. I don't have any w here, and I make the same assumption on a, that it is positive everywhere. And so now the situation is a bit different, because if u is not 0, then you have both directions. So d1 is t of m. And if u is 0, you need an extra bracket to generate the missing direction. Because this guy vanishes, and so now you need to compute x1, x2, which is a. So remember that u is 0, a of 0v dv. So in both cases, this bracket generating condition is defined. So I will let this definition here, and I will give you this here, so that if you want to compute things on this example, you can do it. So that's not bored. Okay, so I have a generalization of Riemannian geometry, and I want to do spectral geometry, so I want to understand. So I have an operator, I want to understand eigenvalues of this operator, so maybe I should say it right away that this operator will be self-adjoint and with compact resolvent, so that it has a nice spectrum, and then when it, a nice spectrum of eigenvalues, and what you would like to understand is, for instance, the counting function, or you could want to understand the semi-classical measures associated with this operator, etc., etc. And I will focus on another well-known object in spectral geometry, which is the heat kernel. So I can look at the heat equation associated with this operator. So the heat equation, okay, heat equation. So it's, you solve the following system. So U0 can be in L2 or in any Sobolev space, for instance. And this heat equation has a kernel. So the kernel I will denote by E. And what does it mean that it is the kernel? It means that if you want the solution to this heat equation, you have to integrate U0 against this function here. So U of t and q of u and t m is the integral over m of e t m m prime u0 of m prime u of m prime. So that's another place where you need to have a volume. So we could define the kernel as a measure, but okay, I prefer to do it like that. And let me just observe that by using the self-adjointness, you can prove that this kernel solves the following kernel equation, which is another heat equation, but on m cross m. So you have 2 times dt, and here you just apply the Laplace operator on the first variable, and then you apply the Laplace operator on the second variable. And what is the boundary condition that you need, or the initial boundary condition? So the initial boundary condition is when t goes to 0, you should converge to the Dirac mass on the diagonal. So this tensor product just means that delta, so E now is a function of t, m, and m prime, and so this one is delta on m, this one is delta on m prime, and if you see, you can think as the Sub-Riemannian structure to live on the product, and the bracket generating condition on each factor will imply that it is satisfied on the full space. And so I will do a bit. Okay. By hypoellipticity, I will come back to this now, or in a few minutes, but by hypoellipticity, I know that this is smooth with respect to all its variables. Hypoellipticity implies that E is smooth. So, and what is the heat kernel approach to spectral theory? Is what you want to understand is the following quantity. So the question is we want to understand the small time asymptotics of something which is like this, if of t, which is the integral of f of q m, f of m, e, t, m, m. So I restrict my my kernel to the diagonal, so it is good to know that it is smooth, for instance, and I integrate with respect to the measure, and you should think of f to be f is smooth, and using a partition of the unity, since my manifold is compact, I can restrict to think of m as very localized near point. What I mean is that if I know how to compute the small time asymptotics of this guy for any f localized at any point on my manifold, then I will know for any f no matter what. And okay, So in the Riemannian case, there's a celebrated result that gives you this asymptotic, which is the Minak-Shundaram Pleyel. So that's for the Riemannian case. And there are other, okay, it's a well-known result. It's a well-known result. It traces at least to these authors, but maybe even before. And there are different ways of proving it. I will give you a proof or an idea of proof in a minute. I just want to spend some time to speak about the history of little bit of history of these problems. So there are two sides of the history. So one side is concerned with understanding how the elliptic theory can be generalized to hypoelliptic operators. And there's another side, and inside this, literature, there are some works that are more focused on the heat kernel or what is closely related to the Weil's law. So I will, so I recall, or I tell you, I don't know, that you can recover the first term in Weil's law using the first term in the asymptotic expansion for the heat kernel using a Tauberian theorem. So in this particular case, it will be Karamata's Tauberian theorem. So I will. I have quite a lot of names to cite, and I will tell you what has been what they do inside. So first, probably I should start with Hermander in '67, and so Hermander makes the link between this condition and hypoellipticity. So I haven't told you what hypoellipticity means. Hypoellipticity is the property for a PDE that if the right-hand side is smooth, then the left-hand side is also smooth. So an operator P is called hypoelliptic if whenever PU is smooth, then U is also smooth. And so in this setting, so it was Hermander who proved that hypoellipticity, that bracket generating condition implies hypoellipticity. So I can tell you also that this condition on the geometric side is the condition you need to say that you can reach any point, any 2 points on the manifold can be related using a path that is, whose tangent is always in D1. So a path like that is called horizontal, and so, no, that's not what I said. Yes. So it means that, so this condition, so in control theory, it's sometimes called a Chorachevsky condition, and it means that the manifold is connected by horizontal path. So then there is a harmonic analysis literature on nilpotent group. Because so that's the setting in which Clotilde was earlier this week. On nilpotent groups, you have a structure like that, and so you can try to generalize what you know about harmonic analysis. So there are works by Folland and Rothschild-Stein. So these are really PDE oriented, or not PDE oriented, I don't know, harmonic analysis oriented. So that's maybe starting from the 50s and evolving after that. And concerning the heat kernel, there's a paper by Métivier in 50 years ago, exactly. And what he does is construct an on-diagonal estimate for the heat kernel. So exactly what you need to understand IF of t, using what he calls a nilpotent approximation, which is what nilpotentization is about. And Benarus so he has a condition, a geometric condition, which is called equiregularity, that I will tell you a bit after. And then Benarus in 89 obtains the same kind of estimate, but using probabilistic method. And then there is a school. So at the end of the 70s and beginning of the 80s, so the differential approach has been much popularized. And so the first thing that people looked at were elliptic operator. And then they started applying this machinery to hypoelliptic or to degenerate elliptic, meaning that the principal symbol is not elliptic anymore. So it has a manifold sigma on which it vanishes. And then there are many works, so I will stop writing names because I must be faster. So there are works by Boutet-de-Monvel, Grigis, Helfer, Nouriga, Bolle, Camus-Pham, and huge activity around elliptic degenerate problems or hypoelliptic degenerate using pseudo-differential operators. And this has been applied to derive Weil's law by Mednikov and Sjöstrand, and then by Moram, and each time with different hypotheses on the place where the principal symbol vanishes. One important thing is to know whether this sigma is symplectic or not in the cotangent bundle, and then there's also a question: at what order does the principal vanish? The principal symbol vanish? And so, for maximally hypoelliptic operators, you can look at pages 651 and to 668 of Ivry's book, and you will have some result in this direction. And so more recently, there have been a renewed attempt to construct to understand pseudo-differential calculi associated with this kind of geometry, so by Fischer-Rosansky, Fischer-Fermagnan, Flynn. So if your name begins by an F, you can try to add it to the list. And so using again mixes of techniques from harmonic analysis and from pseudo-differential theory. And I should also mention the work by Androdoudakis, Mosen, and Juncken, the recent work by Androdoudakis, Mosen, and Juncken, who prove the Helfer-Nouriga conjecture using groupoid methods to construct a good geometry associated with this Sub-Riemannian structure. So how do you prove how do you prove the heat asymptotics in the Riemannian case, or one way to prove it. So one standard way to prove it is by constructing a parametrics. And here I will show you a different way, which is also well known. I'm not claiming any novelty here. So, so I'm in the Riemannian case. So my operator, so think that I have local coordinates. So I choose local coordinates centered at some point Q. So for instance, you can think about exponential coordinates at Q, so Q may vary, and so the system of coordinates varies with Q, and then I fix Q, I make computation in this system of coordinates, and at the end I will remember how it depends on Q. So the operator can be written like that, so something very general. So now I'm Riemannian, so this goes from, okay, so my xj are coordinates, so I have d of them, and then I have a first order term because of the metric. So in the Riemannian case, usually you take the Riemannian metric. And now I make the following change of variables. So I note delta epsilon q of x. It's just epsilon times x. And if you compute the change of variables, or no, and you introduce a family of operator, delta of epsilon q, which is the following, which is minus same ij between 1 and d, and here ij, instead of looking at x, I'm looking at epsilon x, and I have here dx xi dxj, and the same thing here, di of epsilon x dxj. So maybe I will denote here that it depends on q, which is the center of my coordinate system. And I define the following thing.
Sorry, Luc, do you want to be in normal coordinates?
What?
Do you need to be in normal coordinates?
No. Here not. No. I don't need to be in normal coordinates because Riemannian geometry is isotropic. So now you define E hat of Tx x prime that depends parametrically on epsilon and q, and this is just epsilon to the d, E. So E is my Hit kernel for my original Laplace operator, and here I just have epsilon t squared delta epsilon q of x delta epsilon q of x prime. Okay, so making a change of variables in PDE is not always a very nice exercise, but in principle, we know how to calculate, and what you obtain is that E hat solves this kernel equation. So the kernel equation associated with delta epsilon q. And this allows you to make the following trade-off. So what you will trade, so you will trade variables for parameters. So what you do, so first, you change the name of T. So you replace it as big T. And then you make T, big T equals 1. And at the same time, you put x and x prime to 0. So at this stage, what I obtain is that E hat of 1, 0, 0, epsilon q is epsilon d E at epsilon square, so T is 1. And here I have delta epsilon q x. Delta epsilon q at 0. My coordinates are centered at q. So delta epsilon q of 0 is q. And same for the other one. And now you put epsilon equals square root of t. And so this gives you the following formula. E t q q is t, so E hat of epsilon q. And now imagine that you have a PDE theorem that tells you that whenever you have a PDE, an elliptic or parabolic, here in that case, parabolic equation that depends smoothly on coefficients, then the heat kernel is also smooth with respect to the coefficient. What you have proved is that the on-diagonal estimate is some power times something which is smooth. And now this is smooth in epsilon q. And now you can integrate with respect to epsilon. So it's not epsilon now, it's square root of t. And now you can integrate with respect to q and do asymptotic analysis, and it gives you the heat asymptotic extensions. Actually, it's a bit better than that, because you're not forced to put x and x prime to 0. And if you recall, so here you will keep x and x prime, and here you will have delta x, delta square root of t at q of x prime. And if you're not too greedy, meaning that your PDE statement, you will state it only on compact domains. What you have here is an asymptotic expansion of the heat kernel in a square root of t neighborhood of the diagonal, which is good. So this is a nice method. So you have to pay the price of proving a PDE statement, but that's how life goes. But it seems to be quite a robust methodology. And so the natural question is whether there exists Sub-Riemannian analogues of these dilations, delta. And it turns out that there do exist such dilations. So, and that's what I want to add to my definitions here. So this is the most unpleasant part of the talk, where I need to introduce all the relevant features of Sub-Riemannian geometry in order to to be able to continue. And so I have a certain number of definitions, and I like the following small book, Control from Frédéric Jean, Control of Non-Autonomic System. It's a very small book and you will have everything you want as an introduction to Sub-Riemannian geometry. So first, I want to compute the growth vector. So the growth vector is just the dimension of the di. R, between 1 and R. So for instance, in the Heisenberg structure, the growth vector is, so d1 is of dimension 2, and d2 is of dimension 3. So the growth vector is 2, 3. So that's the growth vector. Here, it depends. If u is not 0, then the growth vector is just 2. And if u is 0, the growth vector is 1 at the first stage and 2 at the second one. And so the structure is called equiregular. So that was the condition used by Métivier. So equiregular means that the growth vector is constant. So that's the growth vector, and now I have the weight vector. So the weight vector is for an adapted system of coordinates. So as you see, my skills in geometry stop quite fast. I use system of coordinates. So what is an adapted system of coordinates? So you have d vectors, which are the d by dxi, and you want them to be adapted to the flag. So if the growth vector is 2, 3, so the first two coordinates will be in the first two-dimensional plane, and then the third one will be in 3, and if etc. etc. So this means that for each I, you have so for each I there exists some j such that dxi is not in dj minus 1, but is in dj. And then you will say that the weight of the coordinate I is j. Okay, so let's see what it means in the Heisenberg case. So in the Heisenberg case, so UVW is adapted. So U and V are of D1, so the weight of U is of weight 1, V is of weight 1, and W is of weight 2.
Is it 1 point you're doing this?
Yes, yes, yes. Very good. Very good intervention. Yeah. Yes, yes. Everything. So you fix Q. You fix Q, and everything is the growth vector at Q, the weight vector at Q, adapted coordinate at Q, order at Q, and privileged coordinate at Q. And then Q moves. And there's also Q at Q. So Q is just the sum of the WI's. So in the Heisenberg, for the Heisenberg structure, so okay, I didn't say it. So the Heisenberg structure is equiregular. The Gaussian is not. So that's why that the two basic examples. Okay, and So Q for the Heisenberg structure is 1 plus 1, 1 plus 1 plus 2, so that's 4. And Q for the boundary Grouchin is 2 if you're away of U equals 0, and it's 3 if U is 0. So now you have your adapted system of coordinates, and you want to define the notion of order, so non-autonomic order at Q. So you take a function, you differentiate. What is the order of a function at a point? The order in sense of order of vanishing. You take a point, you differentiate with respect to the variables, and you look at the first time you get a coefficient in the Taylor expansion that does not vanish. So you do the same here. So you're not allowed to differentiate in all directions. So you differentiate only in the directions that are allowed. So you have xi1, xij of f at q is 0 for any n tuple, j tuple, and the xi's here are in D1. And if you have this condition, it means that f vanishes at order at least k. At least j. K is my number of vectors. And with that, you can define the notion of privileged coordinates. These are adapted coordinates that satisfy the following additional condition at Q, is that if J is the weight of xi, of the function xi, so the i's coordinate, so for all x in dj minus 1, when you apply x to xi and you evaluate at Q, you obtain 0. So let me, I won't write it, but I will tell you. In the Heisenberg structure, so UVW is a system of adapted coordinates, and you can look whether it is or not a privileged system. And I claim that if U is not 0, then W is not adapted. Because when you differentiate the function W with respect to, what do I want to say? Okay. With respect to U, you will have a term that remains. I have it. Okay. I may have messed. I may have messed up my condition. Okay. What I wrote is here is stupid. So you have a notion like this, and it may be the other way around. Okay, let's put a question mark here. So I'm not sure I got it. I didn't reread the definition, and I may have mixed up the different things. So the thing is that this condition is made to define dilations. So now, in privileged coordinate at Q, so you take a chart of privileged coordinate at Q. So my chart psi Q. So my chart goes from RD into M. So it may be, I haven't checked if it was the correct convention or if it was the opposite convention. But, and what you do is you define delta epsilon Q of X is just, you multiply each coordinate by epsilon to the power of, and then you transport that on the manifold. So that is well known. That is a well-known construction in Sub-Riemannian geometry. So I must say, so there's a question of whether such privileged coordinates always exist. They do always exist. So there are actually two ways of constructing them once you have the good definition. Is either you take the exponential. So the exponential, there's a notion of exponential on the manifold, exponential of vectors, of vector fields. And if you take an adapted coordinate, a system of adapted coordinates, and you look at the exponential of sum of ui d by dxi, this will give you that the ui's form a privileged system of coordinates. And then there is a more pedestrian approach, which is by writing this condition, once you have it right, and it will give you a triangular system to solve. But this triangular system, you will solve it only at Q. It will be, and you will have, and then you will use the local invertibility theorem to say that once you have solved this thing at Q, you can extend it to a system of coordinates in the neighborhood of Q. Okay, so now I will define the same thing as before. So I will define my Q of epsilon, which is, so epsilon, so it's written like that. So it's a pullback of vector fields, which is usually not allowed, but since the delta epsilon Q are diffeomorphism, it's okay. And then you have mu epsilon Q. So there's always this, which is epsilon minus Q, the epsilon Q mu. And now I have a theorem somewhere. Okay, and I define E hat of T x x prime epsilon Q, which is the same thing as before, except that now I have epsilon to the Q, because the epsilon to the Q is the power you need here to have something which is convergent. So if you're in Euclidean, then each vector will have okay. And so, and here you have E epsilon squared T delta epsilon Q of X delta epsilon Q of X prime. And so the theorem is as follows. So I assume the bracket generating condition. That's a standing assumption. I take sigma in M, which is a submanifold on which the growth vector is constant. And then you take Q in sigma. Then there exists Okay. So you have a neighborhood U of 0 in RD. Neighborhood of 0 in RD. You have V sigma, which is a neighborhood of Q in sigma. And you have an epsilon 0, which is positive. And once you have that epsilon hat is defined on 0 plus infinity times u times minus epsilon 0 times v sigma. And for any compact k in u, in 0 plus infinity plus u, then E hat that goes from minus epsilon 0, 0. So you see it as a function of the parameters into the smooth function on K. This is smooth. So it means that you can for instance, you can fix the value here. You can fix the value x prime, and t, and this t here. And here you will have a smooth function of epsilon q, and you can differentiate with respect to epsilon and q. And the proof is the same as in the Riemannian case, modulo small thing. So I claim that E hat solves the following kernel equation. And now you need to extend the PDE statement about smoothness with respect to parameters of such a parabolic hypoelliptic equation associated with an hypoelliptic Laplace operator. But Hermann's condition, so the proof in the Riemannian case and the proof in the sub-Riemannian case will share the same features, is that hypoellipticity, or more precisely sub-ellipticity, allows you to upgrade smoothness in a very low regular Sobolev space to a smoothness in a high regular Sobolev space. So what you need to prove is, first you need to prove a continuity here, but with value in something which is very weak, some h to the minus n. And once you have that, sub-ellipticity will do you the job and will improve it to smoothness. And so that's the major task, and the rest of the proof is more or less mimicking the Riemannian case. So, 5 minutes, okay. So this procedure is called nilpotentisation. Okay. So now I will, I don't know if I can explain what I want to explain in 5 minutes. Let's see. So this gives you Métivier's result, because for Métivier's result, you only need, so you're in an equiregular case. So in this case, you have, in this case, you can take sigma to be the whole variety, and the only difference will be that instead of having t to the minus d over 2, you will have d to the 2 over 2. So let's try to do the Grushin structure and see how it works. So the Brushin structure is like that. So I want to understand IF of t, which is not written anywhere, but which is the integral. So say I take f equals 1 and I want to integrate this thing. So here d mu is just the Lebesgue measure, du dv. Okay, so if I do that, my Nilpotentisation procedure, as in the Riemannian case, will give me something in a square root of t square root of t neighborhood of the diagonal. So here, so I don't care about the things where u is not 0, because here you are elliptic and Riemannian, and so you know exactly what is the asymptotic of this, provided that b is small enough. So now I will look at what happens for u equals 0. So I make the first nilpotentization. So first nilpotentization, which is to set u equals epsilon x and v. So I take a sigma that parameterizes my singular surface, and here I put epsilon squared y, because y is of weight 2. And if I do that, I will have an asymptotic expansion. If I do that, I will have an asymptotic expansion in the neighborhood of size square root of t. So that will give me an asymptotic expansion for this thing. So I want x to be less than c square root of t, and y is between minus v0 and v0. So I want to understand b is my ball here, and what I can do with one nilpotentization is obtaining an asymptotic expression of the integral over this set here, which is of size square root of t. Okay. But if I look at the modified Sub-Riemannian structure x epsilon q, away of this first neighborhood, now I am a Riemannian. And so what I will do a second nilpotentization. And now, so for reasons that appear at the end in the computation, I just need to make it near the point x. So this is an x1 now. x1 equals 1, and y1 equals 0. And here the weights are 1. So what I put, I set x1, which is, so I'm near 1, and I have a second parameter of nilpotentization, and y2 is epsilon 2 y2. And this leads to introduce the following rescale version, which is E double hat. So now I have t x x prime, so this does not change. But now I have two nilpotentization parameter, and I still have only one external parameter, which is sigma. And now, okay, so let's do it. So you write it like this, square t. Here you have, so maybe I will denote it like this. And in the end, what you want to do, in the end, you will make t equals 1, x equals x prime equals 0. But now you have two parameters to play with. And what you will do is that the first nilpotentization parameter, you will keep it as a parameter that will allow you to integrate on this thing. And the second one, you put it what you need to have here t. And remember, and now you recall that since x must be bigger than square root of t, actually this is not singular. It's not singular on your integration domain. And so you do the computation, and in the end, you obtain something that you, so you play the same game, you prove that this E double hat solves kernel equation with parameters. You prove that you can apply your PDE theorem, so everything is smooth with respect to the parameter, and etc. So I will stop here, and I will just comment on two things. So this is a pretty robust method. So if you have a Sub-Riemannian structure which is stratified according to the growth vector, then you will take a point and you will, so at the first nilpotentization you will have a neighborhood of size square root of t. Now, so this can be interpreted at looking at the sphere bundle and looking at the new Sub-Riemannian structure on this sphere. And now this can be equiregular, then it's okay, otherwise it's not, and then near each point you will have weight, and you will do, like that, a sequence of multiple nilpotentization. And this is, and if you want to understand the heat kernel, the leading behavior of the heat kernel, you need to understand all these sequence, those chain of nilpotentization, and see what they give in the end. And so, this is very, very reminiscent of the work by Androloudakis, Melrose. Okay, so this is reminiscent of two kind of works. So one from the Melrose school of iterated blowups and things like that, and one from Androloudakis, Mosen, and Juncken, where they also need to understand, so that geometry is made so that they need to understand all possible way of approaching a point in order to define continuity or what is a smooth function of in their geometric setting. So that's the first observation. And the second observation is that there is a problem with this procedure, is that at each step you need to check that you can apply your PDE statement. So you need to check smoothness, and in the end, smoothness will be true only in regions, and in the end you will have to check that all the regions on which you are able to get the asymptotic behavior cover the whole manifold. And for this we rely on two geometric assumptions. So one is a geometric assumption where everything goes well, and the other is analyticity, and using a preparation theorem that tells you that you can partition your manifold like that. And I will stop here.
Thank you. Any questions?
So I have a simple-minded question about the final answer. If I do this procedure and I have something of Bauer-Grushin type, so there's this sort of deep stratum where it's bad and then a big stratum where it's less good, does the small stratum contribute to the leading order?
So in this case, no.
Does it contribute, I guess?
In this case, no, but it's not a general fact. So indeed, so there is a question which is to know. So you have you have all those different strata, and you want to, in some sense, understand which stratum contributes the most to the asymptotics, and it depends.
Really?
So yeah.
So you
yeah.
could make
But this is known from a long time. This was known to Moram, and this is known in the Mednikov-Strauss case. And so you have three numbers, and you have to compare them. And in the Bauer-Grushin case, it's the equiregular region that wins, and you gain something which is 1 over t log t. You gain a t, log t. You lose a log t compared to the Riemannian case.
So I'm wondering if anything is known about next terms in the heat asymptotics, not the main term, but next term.
Yes, so this method will give you the full asymptotic expansion.
Did anyone compute the first few coefficients? What do they give?
Okay, so I understand your question. So yeah, so that's a very good question. So in this kind of business, there are 2 steps. First step is stating that there is an asymptotic expansion, and second step is saying, okay, the coefficients have some geometric term, have some geometric meaning, and so we have the geometric meaning of the first guy, but not of the other ones. So in the Heisenberg case, this has been done by Davide Barilari, and he has a geometric interpretation of the heat asymptotic expansion in the Heisenberg case.
You have it only in the equiregular case, or you speak about the complete expansion?
Yes.
Do you speak about the equiregular case, or in?
No, we have it in all cases. In all cases where this machinery works, in the end, you have so I can show you. You have to compute the asymptotic expansion of something like that. So you have so say tau is so you have the first nilpotentisation. Tau is bigger than c square root of t, and here you have tau to some power minus alpha, and here you have a smooth function of square root of tau, and of tau divided by square root of t. The other way around. Square root of t divided by tau. T tau. And you have an overall. Okay. And now you have an asymptotic exercise to do, which is to, so f is smooth in all in both variables. And now you can prove that such a thing has an asymptotic expansion. Sometimes you have logs that pop ups, and etc. But you get in the end a full asymptotic expansion in all cases where this method works.
But in this case, you have the so say the boosted case. You have this computation at the point where the and you have to mix with.
Yes. So you have an expansion. Okay, you have asymptotic expansions that comes from 3 different cases. You have the elliptic region. You have an asymptotic expansion using the Riemannian case. You have the square root of t neighborhood of the singular surface, where you have an asymptotic expansion using the first nilpotentisation. And you have so here you know, and here you know. And you have to compare the 3 ones. But it gives you that the statement there is an asymptotic expansion is true. But the computation of the coefficients it's another thing.
All right. So no more questions? Okay, so let's thank Luc.